Duncan Haldane is the Eugene Higgins Professor of Physics at Princeton University, Fellow of the Royal Society, Fellow of the American Academy of Arts and Sciences, the American Physical Society, the Institute of Physics, the American Association for the Advancement of Science, Buckley Prize winner, Dirac Medal, and this year's Nobel Prize in Physics. His topic, Topological States of Quantum Condensed Matter. Please welcome Professor Haldane.
Thank you. I'm going to spend some time, I'm not quite sure how much I will get through, on some nuggets from how the topological states of quantum matter were first recognized and where they're going. And perhaps in the last slide or so, I will actually get to the topological protection that hopefully will be explored by others later. Okay, so before this was discovered, entanglement was kind of a crazy thing that Einstein came up with as an attempt to show that quantum mechanics was just totally crazy. And he was hoping that the attempt to measure entanglement would put a nail in the coffin and consign it to the dustbin of history. But of course, entanglement turned out not just to be a strange prediction, but now it's become the central theme, really, in kind of modern quantum mechanics, I believe, because of its deep connection to information and the possibilities of information processing using entanglement as a resource in the future. And these topological states of matter that were honored this year, both at Nobel and also here, the thing that's special about them that really makes them different is that they involve entanglement in a very profound way. And so, of course, in retrospect, they were strange and difficult to believe when they came up, because we weren't used to having things in which entanglement was a key, on a scale larger than an atomic scale was important. Okay, so as I say, entanglement is kind of part of chemistry when it's in a valence bond, but it becomes strange, as Einstein thought, when you start to get things which are spatially separated by more than this tiny atomic scale and still have this long-range entanglement. So the basic model, of course, is the spin singlet bond. So as I say, the quantum mechanics passed all its tests, and the basically laws of quantum mechanics have been known since the early 30s or late 20s. And they've always passed everything that's been thrown at them, but there's a big difference between knowing the laws of quantum mechanics and knowing the kind of strange things that it allows to happen. Same thing with Maxwell's equation. Just writing Maxwell's equations down doesn't allow you to immediately glimpse all the possibilities of that electromagnetism can lead to. So anyway, so this is the statement. So as I say, the discovery of this stuff was really because it had strange properties, and now we know why it's strange, right? It's strange because it's topologically different from the usual kind of matter that we were used to before. Okay, and some of the exotic properties these unexpected states of matter have, they very typically exhibit, say, fractionalization of expected units of charge or spin that are carried by excitations. And another feature is the very widespread presence of robust edge states, interesting degrees of freedom at the boundary between topologically non-trivial matter and ordinary matter. And other things, you find these very non-standard exchange or braiding statistics when you start to move the topological defects of these this matter around inside it. And of course, that's given rise to the dream of topologically protected quantum computing, by allowing you to, in principle, store and process information in a way that's somehow hidden from the environment. Okay, so one of the really early examples, so this work is kind of, a lot of work from the 1980s has been being honored these days. In fact, even the Kondo Effect, which was another thing that was solved the exact solution of the Kondo effect about that time, got a prize this session. So somehow all this, I think you can date 1980s to be about the time where thinking in condensed matter physics changed. The kind of physics I teach now has got very little resemblance to the condensed matter physics that I learned as a graduate and undergraduate. I learned all about band structures, muffin tin potentials, all kinds of things that you never heard of now, which are all the details of trying to do complicated a priori calculations. But in fact, that missed the point of the details, and somehow the topological matter means that the details are not important because everything is robust. And we can actually focus on calculating simple model systems which exhibit the physics we want to find. So the key in this thing has always been finding the right model system that you can actually take apart and exhibit all the deep mathematical underpinnings of the subject, but see it in little calculations that you can actually do explicitly and understand what's going on. So, okay, the one-dimensional spin chains at the time were kind of an exotic thing. People had started off because there were exact mathematical solutions of these things from the 30s, and there was starting to be interest in organic materials which had long chains, but really they were toy models. They were supposed to be the thing on the step to higher dimensions where the real physics lay. But what we've really realized that these lower dimensional systems, they're much more profoundly influenced by quantum mechanical fluctuations, and they have some of the most amazing properties in their own right. And in fact, but now we've gradually stepped up from 1D to 2D to 3D topological matter. And of course, many theorists are stepping up to 4, up to 8 and 10 dimensions too, but I won't discuss that. So the symmetry-protected state, symmetry-protected topological state of the quantum Heisenberg antiferromagnet. Well, this is something which shocked people in 1981 when I predicted it. It shocked people so much that they kept on referring to it as a conjecture, implying it was something just fished out of the air with no validity. But of course it wasn't. But basically, I stumbled over the fact that the actual properties of the quantum spin chain when it had an integer spin was quite different from the known properties for the mathematical exact solution when it had half-integer spin, which sort of vaguely resembled the semi-classical spin wave theory at very large indeterminate spin. So people gradually thought there was just some kind of continuous dependence on a spin quantum number. But spin is not just a real number. Spin is a fractional number. It's either integer or half integer, and that's a topological statement. So spin in this context, spin in the theory of these things enters in one way that 1 over the spin, which is basically not a topological number, controls somehow the degree of the quantum fluctuations in the system, but there is actually, the topological part depends exactly on whether you're half, 3 halves, 2 halves, 1 or 2, etc. So anyway, so this was a surprising thing, and again, to actually understand it better, the toy model approach turned out to be the key thing. That this conjecture, this idea was basically made very explicit by the use of a toy model called the AKLT model by Affleck, Kennedy, Lieb, and Tasaki. And actually, that model turned out to have been one of the driving forces for the development of the density matrix renormalization group, which is the precursor of matrix product states and the whole business of fractionalization, of entanglement in quantum condensed matter. So partly this was driven just by the attempt to prove or disprove or otherwise this so-called conjecture about the spin chains. Well, now we know this seemed to be a kind of very kind of esoteric thing at the time, but now we know from the work of Xiaogan Wen, who's one of these, who was honored today or yesterday, we know the ground state of this model should actually be classified as a symmetry-protected topological state. And in some sense, according to Xiaogan, it's the hydrogen atom of topological matter, the simplest possible example of non-trivial matter. And so let me talk a little bit about the toy model, the AKLT model state. This replaces the, let's go back. So the actual model, which is pretty good physically for organic materials, is that spins typically interact by this exchange process, which if it's the kind of exchange that Anderson discussed, it's a S dot S, a kind of a simple natural model. But what, let's find out. But what the AKLT model did was it actually is extremely reminiscent of what earlier work I had actually done on the Laughlin state. But again, instead of taking the complicated Coulomb interaction in a Laughlin state, it turns out you can throw away large parts of the longer range part of the Coulomb interaction and keep only the short range part, and that makes the Laughlin state an exact eigenstate of a very special model. So, having a very special model where these topological states are exact eigenstates is actually a tremendously helpful thing. They're slightly simpler than generic models, but they allow you to show things up. Well, the AKLT model noted that if you have two spin 1s, they can combine into 0, 1, or 2 for the total spin. And the generic antiferromagnet has 2 at the top, 1 in the middle, and the singlet state of the bond at the bottom, the one which is why it wants to be in a Niel state. The AKLT model drags the second level down, the spin 1 level down, until it actually becomes degenerate with the spin 0 model, spin 0 level of the spins, which is a special case. It's actually a transition point to a disorder point where something incommensurate happens, because when the spin 1 level is lower than the spin 0 level, it actually frustrates the Niel state. But dragging that down turned this model into a simple projector. And each bond has a projection operator on it, which has a kernel, a zero energy state. And the marvelous thing is when you add lots of these bonds together, the total Hamiltonian still has an exact zero energy state, just as in the case of the Laughlin model. And these are special. So the AKLT state allows you to, I won't really give full details on it, but basically the thing is you can organize the system into valence bonds where every spin 1 basically has 2 valence bonds, one hanging out on either side of it, like a pair of hands, and it handshakes with the neighbor to the left and right. And its valence bonds are totally used up, but when you get to the end of the chain, there's one left over at one end and one left over at the other end. So the zero energy degrees of freedom of this model are these disconnected, widely separated free spin 1/2 degrees of freedom. But if I fix the spin degree of freedom at each of the chain, I kind of put them in a definite state, I first have got this example of fractionalization. The thing was built up of spin 1 objects, but somehow it fractionalized into spin 1/2 at either end of the chain, which is the boundary between the regular matter and the strange matter. It's a very typical feature that you have an edge state with non-trivial quantum numbers. And if I do an entanglement cut, basically I do a Schmidt decomposition by kind of writing the wave function as a product of something to the left of the degrees of freedom to the left of a cut down the middle of a bond and the left degrees of freedom to the right of a bond. The AKLT model state can always be written as a matrix product between, there's a basis of 2 states on the left, 2 states on the right, and this 1, 0, minus 1, 1, 1, 0, 1, minus 1, 0 Tor matrix, the permutation of matrix. And so intrinsically, wherever you cut the thing, provided there's more than one bond in the problem, there's the same kind of entanglement between the 2 ends of the chain as there is in the chemical valence bond that's existing in a simple covalent solid between the 2 electrons which are locally at the same place. But this chain can be very long, right? Of course, it doesn't matter how long it is because this is a topologically protected structure. It's kind of like a bar magnet. I cut the thing in half. I'm always going to get a north pole and a south pole. I cut this system in half. The entanglement will always force these kind of edge states on you. And this is a very typical, surprising feature. So it's robust. And of course, the real model, where you put back, you switch off this very special fine-tuning to get the standard model. It has a more complicated entanglement spectrum, lots more levels in it than this one has, which is a single spin-half kind of doublet. But every other, all the entanglement levels in the full system, when I cut it, they all are twofold degenerate. Well, if I take a normal piece of matter, chop it up, and look at the entanglement between the spectrum of the Schmidt spectrum obtained by disentangling the two parts. They'll just be all levels will be non-degenerate. Okay. So again, you feel this very special protected feature. And this is really almost the same thing as Einstein-Podolsky-Rosen. It's just not two photons shooting off down a light tube across the Atlantic Ocean or something, but they're two spins at the end of a chain that's inside condensed matter. Okay. Okay, so let's get back down to, again, the story of regular versus topological condensed matter. So before all this came up, we basically knew about broken symmetry states, like a solid as compared to a liquid, but also various magnetically ordered states inside the solid. And these things have conventional solid order. They're classified by Landau-Ginzburg theory. If you want to investigate it, solids, there's always a first-order transition because there's always a cubic term. So there's a whole law about what kind of transitions can be first-order, what can be second-order, etc. But there's really nothing special to do with the edges of the solid, right? It's the bulk that's somehow different. The bulk of the solid is different from the rest in an obvious way by having order. But when you get to topological states, maybe the paper, the portrait example of this is the quantum Hall liquid state. There's no broken symmetry in the interior that distinguishes it from the exterior, but the interior is quite weird. And what you have going around the edge of this system, very typically, is a one-dimensional edge band and this puddle of electron fluid, which has the amazing property of being chiral, that it moves in one direction only. It transports energy and charge, etc., just around in a particular sense. And this is, again, so when you look at the interior, what is it that's different? Okay. Well, topological matter generally have something. Why it's topological is basically the different classes of matter can be labeled by whole numbers. Okay. A set of and the trivial matter, those whole numbers are probably something like trivial like 0 or 1, depending on which classification is being used. And the basic point is whole numbers cannot change continuously. And so this means this whole topological stuff is much more stable against dirt, defects, or anything. Well, if you make, silicon wafers have to be made ultra clean for making today's computers on them, but a little speck of dirt will ruin a whole wafer. But here, this stuff is robust because a little speck of dirt won't ruin anything. You have to do something violent, like shoot a hole in it or something, to change its topology. So the classic example that was being used all the time at which confused, I think, a lot of people at the Nobel Symposium this year is the classification of closed surfaces by the genus or number of holes in them. I mean, if a shape such as a sphere which has 0 holes, it can be distorted by small forces. You can change a soccer ball into an American football, but you need a violent event to drill a hole in it to cause it to turn into a donut. And of course, there's no such thing as 0.3604 plus or minus something holes. So this makes the measurement process a lot easier. It's a yes or no, a Boolean choice. So experiments to determine whether something is topological or not, I mean, it don't depend on very careful measurement of things. Okay. So again, topology and geometry were related back in the beginning of the 19th century by this amazing discovery by Gauss, who thought this was the most amazing thing that he discovered in all his mathematics. He discovered that if you integrated the curvature of if we know the curvature of a sphere is Gaussian's curvature is 1 over r squared, and if you integrate the surface 4 pi r squared times 1 over r squared, it's equal to 4 pi. But Gauss discovered that he could change the surface of the sphere into something, to a banana or a football or whatever, and the answer was still 4 pi. And then he found out that if it had holes in it, the answer was different. And this is a thing that's probably plaguing all the talks about topological physics these days. Everyone puts in the movie, which I'm not going to show, of the coffee cup changing into the donut and back again. They should at least get some more interesting cups to change. Okay. So, as I say, before 1980, this stuff was unknown, and it took a long time to really understand these things were unusual. I didn't understand that there was topology floating around, in fact, deeply connected to what Mike Kosterlitz had found in classical physics. The spin chain work was initially found by mapping the Kosterlitz-Thouless process from statistical mechanics into space dimensions to one space and one time dimension for a one-dimensional quantum system. And there were additional features that the Boltzmann factors are always positive in classical mechanics, but they can be positive or negative in time reversal invariant quantum mechanics. So this stuff came from topological stuff and had a lot floating around in it. There was field theories with terms, but really it took a long time to really understand that the stuff was basically a topological classification of matter. And we're finally really finishing some of the simple states of achieving a unified understanding of this. So for example, one of the surprises of this topological thing was the quantum Hall effect, which was people, von Klitzing initially, and then in the fractional case, Sui and Sommer and Gossard. They found that the whole voltage was tied in a very fundamental way to the current flowing through the sample by basically a rational number, 2 integers. And initially, this was a mysterious thing. Why was this so accurately quantized in low temperatures in a non-uniform sample? And people started looking, well, maybe there's a relativistic correction to this. People started getting large calculations and to try to see maybe, as a v squared over c squared floating around in here. Not at all. It turns out it's got, as you can see in the formula, at least when it's written in SI units, which are the only ones I will permit myself to use, there's no speed of light floating around in the definition of the conductivity quantum, which tells you this has got absolutely nothing to do with relativity. But as I say, it turned out that this was a topological state. And in fact, now we can see that anything with integers in it, that it's got to be topology behind it, although it wasn't known at the time. And in fact, the stability of the thing, the only corrections to this are due to a finite size corrections due to tunneling across the weakest link for tunneling from one side of the sample to the other will give you exponentially small corrections, but as you make the sample big, the law of exponentials kind of means that all those effects have gone away completely once you've gone beyond some length scale and width. Okay. So, this is a talk. So this of course comes from Landau levels. In the simplest case, the integer Hall effect is simple Landau levels, and we have a spectrum of Landau levels which are now flat in a uniform system with a clean background, which was the theorist's toy model. The Landau levels are completely degenerate, and there's one Landau level for one Landau orbit in each level for every quantum of magnetic flux. So it seemed at the time, if you just fill the lowest Landau level completely, and you'll exactly get the predicted formula, the measured formula of von Klitzing. Of course, the mysterious feature then was this requires you to get the magnetic field absolutely perfectly right, even if you have this clean sample, and it would only occur at one particular magnetic field and not show a plateau. And a lot of effort was devoted to understanding the localization properties and the modification of localization by the usual localization theory in this context to kind of understand why it occurred in a range of fields. Okay, so there's the picture of the filled Landau level at a particular field. It needs fine-tuning. But actually, it's topology that saved the day. And this is something that actually David Thouless stumbled over. But initially, we see that when you actually consider the edge of the system, there's naturally, as Bert Halperin pointed out, if the Landau orbits are going in the clockwise direction, there's a counterclockwise, which is unfortunately is the convention being used in our field. There's a counterclockwise edge mode, which is winding around the edge of the sample. And as you get to the sample, the levels inside the Landau level, the states inside the level are pushed up. So you naturally get a Fermi level to be pinned at the edge, and you no longer need fine-tuning. It wasn't really realized at the time, but this is a fundamental topological reason. We don't need to put dirt in. We can have the thing in a perfectly clean sample, provided it's got edges. And all the dirt does is make the edge wander around through the sample at some point, which depends on lots of details. So David Thowles and Komoto, Nightingale, and Nyes came up with that. They actually had the kind of brilliant idea to go to a toy model. The model of dirt, which involved all the issue of localization physics, which we're only kind of groping with now again in many ways, is much simplified by replacing it by a simple sinusoidal potential, which turned out to be the Harper's model. And then they could actually solve it by going to, this of course is in no way related to the real system. There was no, people have been trying to make the Hofstadter lattice in real systems and maybe succeeded in cold atoms, but this was a toy model, and what they found, because you can calculate periodic potentials a lot better, they found the Kubo formula could be put into a marvelous form, which is an integral over what Barry Simon, the mathematical physicist, immediately recognized, or after staring at it a bit, recognized was an integral of a curvature associated with Berry's phase. And this actually just immediately related, the TKNN formula was just seen to be precisely a formula, the Chern's generalization of the Gauss-Bonnet formula from physical 2D surfaces embedded in 3D Euclidean space to a much more abstract mathematical context of U1 fiber bundles on manifolds, etc. But it's essentially the same as Gauss-Bonnet, but deeply mathematized and made more general, which is, of course, what the mathematicians do for us. So this was the first time this actually showed that topology was actually the root of all these things, and it really probably, and in fact, although this formula thing was around, it was not until about 1998 that I realized that the TKNN stuff, I didn't actually come to it from TKNN, but I realized that you could make a quantum Hall effect in zero magnetic field. So we have these things called the Chern insulator, and they have marvelous things called edge modes. You can do things that make microwaves go around obstacles, which are microwave versions of all this stuff. This thing generalized to topological insulators with Kane and Meili. And I will just show you one thing, since I promised it at the end, get rid of a quantum Hall. We actually can find, oops, okay, here we are. So the quantum Hall state has nice things, but some of the more interesting quantum Hall states are non-abelian ones, due to starting with Moore and Reed. Qubits have internal degrees of freedom that are hidden. And this is an example, finally I show that for the half-filled lambda level quantum Hall state, which occurs when you have broken particle Hall symmetry, it has excitations which carry 1/4 of a charge in essentially a Majorana modes. And we know that if we fix the total fermion number, make the Majorana, and we have 4 of these things, there's a hidden place we can hide information. And in fact, you can see from this that when the objects are close enough together, as they are in some small calculation, you can actually see the vague difference between the 2 states of the qubit. The qubit is not totally immune to being have its information destroyed by local measurement. This is the charge density for the two states of this qubit. But there's little exponential wiggles in the charge density, but as I make these things become far apart, just like the distance between the edges in the quantum Hall state, we get more and more topological protection of the qubit. And I guess, so this is probably what I wanted to get to at the end. So we see in this thing that there's actually length scales in these problems that determine topology will dominate in the limit where the microscopic length scales are small compared to the distance between the various components. And of course, we're going to one of the dream is to braid these things around each other and process the information. To actually measure it, we probably have to bring them close together, which is a dangerous point. But at least we can make lots and lots of braiding when they're far apart and do this in a topologically protected way. Okay, I guess, how much time do I have? Nothing, right? According to that clock.
Actually, you probably have an infinite amount of time until they turn my sound on.
Yeah.
Now that I have my sound on, you don't have any more time.
Okay, good. Okay, so I'll get to, so anyway, so the, part of all this stuff, you start to see things like Fermi systems. You kind of would filled orbitals and empty orbitals, and you end up, the topological states now have generalizations of fillings of Fermi systems where you have curious patterns called exclusion statistics. there's all kinds of great stuff coming out of this, and it's all robust. And I think there's a great future in store for the future, which I've only touched on the brief tip of it, of topological quantum matter, especially in condensed matter and also cold atoms. Thank you.
Thank you very much. So I'm asking for questions for Professor Haldane. And if you do have questions, it'll be essential for you to come up to the question mics, which are positioned in the aisles. But unfortunately, they're positioned up towards where I am. So if you're at the back, run. Questions? I don't see anybody at the mics, nor do I see anybody running. Oh, excellent.
Yeah. I want to just clarify one thing. You mentioned that the disorder. So disorder is not, even if you have zero disorder, you can still have long this plateau, because the way I learned is, if you make the sample really, really clean, then the integer plateau should become quite tiny. But earlier in your talk, you said that because of the edge, the sample can be completely clean, but still you can have this long plateau. So could you clarify?
Yeah,
that?
I mean, the theorists prefer to study these things where there's actually a clean gap in the bulk of the system. And of course, the real system, when you put on sufficient dirt, you start to make little islands of different quantum, islands of empty and filled states, or different kinds of quantum Hall droplets. So it gets more complicated. But in fact, all you need to go back to the clean system is to have the edge states save the day. And that probably was the insight that came out of and it was a topological property. We knew about the edge states from Bert Halperin, but the Fowler's formula kind of showed that this actually was a topological index in the context they look at it. And the edge states are not just a cute thing that happens, they're a necessary and fundamental part of the topological matter.
So you're saying that then even if the sample is, so you don't need really disorder?
No.
You don't need disorder, okay. Thank you.
There's no states at the Fermi surface in the bulk if it's clean.
Other questions? Do you have a question? Yeah. Please go to the mic. No. Oh, you want to take mine?
Yeah, thanks. Is nu equal half a Fermi liquid or what it is?
It depends. The nu equals half in the lowest Landau level is a Fermi liquid of composite. The basic objects in fractional Hall effect, in my view, are composite bosons, which are the basic object is the analog of the unit cell in a solid. The basic entity in a quantum Hall liquid is a vacancy, which is flux attachment with some charge built in. It's very analogous to a unit cell, and there has to be a boson to have a quantum Hall state. If the object you make is a fermion, which it is by a size 2 hole with 1 electron in it, if that's the basic object, which happens at the half filling in the lowest Landau level, it turns out then there's a Fermi liquid of these kind of dipolar states. Yes, it's a kind of Fermi liquid, but not of electrons. It's a Fermi liquid of composite objects.
So we have one more question over here, please.
Yeah, one more question. So there was recently kind of a breakthrough in topological condensed matter by observation of biofermions and biosemi-metals. Right. And also some science of Majorana fermions in some kind of systems. Yeah. So how would you estimate the perspectives of the applications of this?
Okay, I mean, I have great hopes for applications, but I'm not going to tell you how to use them. These, of course, themselves are Majorana fermions. There's a Majorana zero modes. They're proposals which are somewhat easier to produce in indium antimide nanowires. But in principle, if one can make some of the more exotic quantum Hall states, like the so-called Reed-Irizarry state with Fibonacci anyons, which is not this one, has a more interesting non-abelian states, you can do a lot more with these states. And of course, the hope, the realization that it's at least in principle possible for numerical simulations to produce fraction, just as you can have integer quantum Hall effect with no magnetic field. In principle, one can have fractional quantum Hall effects without a magnetic field, and just from Berry curvature effects, that one may be able to have these more exotic things. But yes, there's lots of the Weil semi-metals is not a gap system, but there's still important topological properties there too. And so again, this was something that you can see in some of this early work coming up, and you can actually see in the 2D graphene, the edge modes of the Weil, the 3D version, the Fermi arcs are present as edge states connecting Dirac points when viewed on. So there's a huge amount of topology to be discovered. These are probably, where it's gapless, there's a connection between topology, and there's also geometry of Berry phases playing an important role.
Well, thank you, Professor Haldane.